As Bill said, I'm at the Allen Institute for AI. I'm totally impressed, by the way, by the wide range of countries that are represented here. So it's an honor to speak to you, particularly people over in India and that area where I think it's like late in the evening at the moment. That's pretty awesome. I'm excited to have a chance to connect with you and tell you about the work we're doing. The title here, Towards Teachable Systems, and more precisely, Teachable Reasoning Systems, it's a little bit vague. We've been doing work in natural language question answering with two goals. The first is having systems not only answer questions, but explain how they came up with their answers in a systematic way. And then secondly, having users interact with those explanations to try and teach the machine when it goes wrong. And then let me just add as well, as Bill says, I'm happy to take questions as I present. So feel free to type that into the chat as I go. And let me just check I can actually see the chat here. So what do I need to do to make that visible? Let's have a look. Just give me 1 second now. I'm just looking to see how I can. So I don't see the chat window myself. So Bill, I'll rely on you to point out if somebody's entered something in the chat.
Okay, yeah, no problem. I can moderate that.
All right, sounds good. All right, so let me just start by just giving you a bit of background about AI2, where I'm from. So AI2 is a not-for-profit research institute. It was founded by the late Paul Allen, the co-founder of Microsoft, about 8 years ago. And its mission is to do AI research for the common good. So you can think of this as kind of scientific philanthropy. We're a leader in computer vision, natural language processing, deep learning, and we have currently about 150 researchers and engineers staff. We're based in Seattle in the United States, so this is Seattle on one of its nicer days. AI2 is this nice building down here, so this is where we hang out. With the pandemic for the last couple of years, I've actually spent most of my time at home, so this is more where I've been the last couple of years in this basement, not very well lit basement. So just to give you a visual of where I hang out, and this is where I'm talking to you from right now. We have 5 big programs at AI2, and one of those is called the Theristo Project. That's the one I manage. Its focus is on machine reasoning and explanation and answering complex questions. We have about 12-ish research staff and program leads, and we have a healthy flow of interns that come in and out through the system. And I should add, we are always interested in hiring. We currently have open positions in Theristo. So if you're looking for an exciting research environment and you're doing leading edge research, please contact me. We're always delighted to chat with you. So let me just start with the big picture of AI. So if we want to build AI systems, they necessarily need to have lots of knowledge about the world, and we would like them to also be able to reason, that is, draw conclusions that validly follow from things they know. And in the old days, how did people build these systems? Well, somebody would hand code knowledge about the world in some formal representation, like Prolog or some other rule-based language. And then to use it, people would take a question and convert it into a formal representation. And why do all that work? Well, the reason is because we have well-defined reasoning engines that can deduce valid conclusions based on the knowledge that they have. And so this was the prevailing paradigm in AI for many years. I spent the best part of 30 years of my life working in this paradigm. 10 years ago, that's all changed, and the kind of modern picture of AI looks a bit more like this. It seems now that we can funnel a vast amount of knowledge directly into large-scale language models, and then with a bit of fine-tuning, teach them so we can pose questions to them and get answers out. And these systems work extremely well. In fact, they work considerably better than the systems that we used to build by hand. So that's great, but at the same time, we've lost something. That is, we don't have a clear understanding about what's actually going on inside these neural systems. And you might say, well, they're kind of performing very well. Why should we care? They're giving us great answers. And so I want to give you just 4 quick reasons why we should care about the reasoning itself. So the first and most significant is that language models can make catastrophic mistakes. That is, they can reach conclusions that simply aren't warranted by the things which they've been exposed to and by the things they know. And this has been well documented. There's many papers that study this. And then secondly, worse than that, language models can't explain why they arrived at their answers, which makes them hard to trust. And then if we can't understand what they're doing, it makes it very difficult to correct them and fix problems. And this is in stark contrast to the way people behave. You know, we're able to provide explanations for our answers, and if we've got an error or a misunderstanding in those explanations, somebody can argue back and correct a fact, and then we might change our minds. We'd like our machines to be able to behave in the same way. And then finally, just thinking about the bigger picture of AI, it seems like any intelligent system should be able to explain what it's doing and react appropriately to new information and correct itself. This is something we'd like our system to do, and the current black box neural systems are not very good at that. So it's important to go beyond the black box systems. So what I'm going to do is talk about some super exciting work that's just about to be published from AI2 that we're working on. And the basic goal of what we're trying to do is, instead of giving a neural system a question and getting an answer out and then you're done, we're looking for a more interactive setting where a user can ask a question, the system can explain its reasoning, the user can ask for clarification and maybe more information. And if the system has got an answer incorrect, then the user should be able to volunteer corrective information and identify why the system gave the wrong answer and fix it. So that's kind of what we're aiming for. And I should say, you know, we're not at the conversational stage yet. So we do have an interactive system that gets one step towards this, but this is the dream of what we are aiming for. And so I'm going to present the work in 2 parts. The first part, which is really a prerequisite for any kind of intelligent interaction, is training models to reason systematically and explain in a faithful way what they did. And then the second part is, given that, how can users interact with the system and teach it new things without having to just shovel in large amounts of training data and hope that solves any problems the system has. So first of all, training models to reason systematically. So do language models already reason systematically? That is, can they take a sequence of well-defined reasoning steps from what they know to produce an answer? Again, there have been studies on this, and the general verdict is that they can't really reason systematically, at least not out of the box. So for example, this is a question we gave to one of our state-of-the-art question answering modules, systems that we play with, called Macaw. So here I asked, what happens if I drop a glass on a bed of feathers? In this case, the system got the answer wrong. It said the glass will break. But more problematically, if we ask the system to generate an explanation for why it came up with the answer, it produces a couple of related sentences. So here it says, because feathers are soft, and if something breaks, then it will shatter. But this really isn't a systematic description of how it came up with the answer. Instead, what we would like is a system that, when I give it a question like that, well, first of all, we'd like it to get the answer right, of course, the glass will not break, but we would also like it to provide more of a chain of reasoning that's more convincing about why that answer should be true. So here, the system said, well, feathers are soft, and if an object falls on something soft, it will not break. So this would be a good chain of reasoning. And so language models out of the box don't do this. So for this first part, our goal was to try and retrain a language model to have this kind of behavior. And of course, like any machine learning problem, to train a system, we need a lot of training data. And so about a year ago, we constructed a new resource called Entanglement Bank. And this is a large expert-created data set of examples of the kind of systematic chains of reasoning that we would like the system to produce. And so just to give you an example of what's in Entanglement Bank and what we asked the annotators to do, we gave the annotators, first of all, a hypothesis like this one: eruptions can cause plants to die. And then we also gave the users a set of relevant sentences to this hypothesis, which were pulled out of a set of textbooks about science. And then what they had to do was to arrange a subset of these sentences into one of these structures, which we call an entailment tree, which is meant to show how the answer, the hypothesis, necessarily follows from the facts which were given. So in this case, what the users filled in here is they've said eruptions produce ash clouds, ash block sunlight, therefore eruptions block sunlight. And then because plants will die without sunlight, it follows that eruptions can cause plants to die. So this is an example of a proof supporting a positive hypothesis. I just noticed in the chat here, somebody asked, what would be a good chain of reasoning for the wrong answer? I'm just going to defer that question. That's a great question, and I'll return to that in just a second. But that's something that the system can try and do as well. Anyway, we collected this data set of entailments. We collected about 2,000 examples of these with about 5,000 of these atomic inference steps in. And now the next stage is to try and train a model to reproduce this kind of systematic reasoning. And so our first attempt at this was to try to do this end to end. So the input here would be a hypothesis, and then a set of relevant sentences that we might have retrieved from a textbook or from the web. And then we wanted to train T5 to generate a entailment structure like this one. And when we tried to do this, we were not very successful at being able to do this for two fairly challenging reasons. First of all, just the information retrieval problem of extracting the right relevant facts from a corpus is formidable. And secondly, these structures can get quite big and complex. And even with the modern language models, they still make errors as they generate these kind of things. So what we ended up doing was to modify the training regimen in three important ways that I'll describe now. So the first thing we did was, instead of generating a multi-step tree, we just had the language model here, T5, generate the top level chain of inference here. So here, given the input, it says, well, because eruptions block sunlight and plants will die without sunlight, it follows that eruptions can cause plants to die. And if you look carefully, you can probably see we actually can generate multi-step trees by then calling this model recursively. So a user might say, well, why is it that eruptions block sunlight? And again, the same module can produce another chain of reasoning for that fact, and then we can connect these things together to generate these multi-step explanations. So we ended up with an architecture where, instead of a language model trying to do everything, the language model just does the basic single inference step, and then a controller wraps around that to generate these multi-step trees. So that's one thing we did. The second super interesting thing we tried was we also tried masking out some of the required facts, and then again trained T5 to generate its proofs. And remarkably, even if a fact was masked out, it would do its best to fill in the gaps. So in this case, I masked out the fact that producers will die without sunlight, and it filled in something similar. Plants will die without any sunshine. And what's happening here is the language model is essentially articulating some of its internal knowledge about the world to try and construct a coherent proof for an answer. So this is kind of remarkable, this kind of generated text kind of coming out of thin air. It's actually coming out from the language model's pre-training to complete this proof. And then the third thing we did was we tried also training the system with examples where we just provide the hypothesis and then asked it to generate as output a one-step chain of reasoning. And again, the system was remarkably able to fill in premises that entailed the hypothesis, essentially articulating some of its knowledge. So at the risk of over anthropomorphizing what's going on, you can imagine T5 as a language model which contains lots of innate knowledge about the world. This is knowledge that it's picked up by essentially reading the web during its pre-training. And what it's done now is kind of materialized a few facts from within that that together entail the conclusion that we're interested in. So this is exciting because it's starting to give us an insight into some of that latent content within the language model that relates to a conclusion we're interested in. So we tried training a system to do this, and it works reasonably well. Let me just give you some examples of its behavior. So if I ask it, do plants require CO2 to make their own food? It comes up with this nice chain of reasoning. It says, well, plants require CO2 to make their own food because a plant requires CO2 for photosynthesis, and photosynthesis makes food for the plant. And it doesn't have to be in science. I could ask something else like, explain why leaving dirty dishes in the sink is a bad thing to do. It gives me an explanation here. Leaving dirty dishes in the sink causes bacteria to grow, and bacteria growing in the sink is a bad thing. So this is another nice chain of reasoning. But because we've trained it only on positive examples, it will also generate chains for false statements. So this relates to this question that Alexander just put in the chat. So here I've given a false statement. So I asked it, give me a chain of reasoning why rabbits have 6 legs. And it happily goes off and does so. It tells me, well, a rabbit is a kind of animal, and animals usually have 6 legs, a fact which is clearly false. And in fact, this is also a fact which the language model itself doesn't believe. So we can test this by a sort of self-referential query. We can ask the language model, do animals usually have 6 legs? And here the system says no. So in other words, at least in this case, it doesn't believe what it said. And this offers the suggestion that we can improve this by adding a verification step where the system not only generates a sequence of tokens, but then checks that those sentences it's generated reflects its own beliefs about the world. So for instance, the system will first of all ask, do I believe a rabbit is a kind of animal? It asks itself that and says, yep. Then it asks itself, do animals usually have 6 legs? And it says, oh no, I don't believe that. As somebody's pointed out in chat, by one count, animals do have 6 legs usually, if you think most of the animals in the world are insects. But colloquially speaking, we normally think of the different species of animals as having 4 legs. So there's definitely some fluidity in the meaning of these statements. And then the third step of verification is to say, well, does the system believe this reasoning itself? In other words, if it were the case that 1 and 2 were true, does the conclusion follow? And here it says yes. So because this verification step has failed, the system would reject this proof. And to make sure it hasn't missed any other proofs, what we do is we overgenerate a collection of different proofs, and the system searches to see if any of those conform to its own internal beliefs about the world. And if it can find one, it says, okay, I believe the hypothesis. And if it can't, it says, well, that hypothesis must be false. So just to show that on a slightly different example, so for this question, the forces that hold Earth in orbit, is that magnetism or is it gravity? First of all, the system converts that question into different hypotheses to check. So is it true that magnetism holds Earth in orbit? Is it true that gravity holds Earth in orbit? Then it generates these candidate chains of reasoning. So here's some chains of reasoning that try to imply magnetism holds Earth in orbit, and one for gravity. And then it tries to verify these and decide, do I believe these? So I'll just read this one about magnetism. So one chain of reasoning for magnetism is magnetism holds Earth in orbit because gravity causes Earth to orbit the sun and magnetism causes gravity. And when it checks that against its own beliefs, it says, well, actually, I don't believe magnetism causes gravity, so I don't believe that proof, and so we'll reject it. And similarly for the other ones. And so finally, the system will select the answer which is supported by a chain of reasoning that it believes. And we can also do this in a more continuous way. We could score these proofs and pick the one that the system believes most strongly if there's more than one that's produced. So this is super exciting. And the reason this is exciting is because we now have some insights into some of the previously hidden knowledge beliefs that the language model had and how they can be combined to support an answer which the system gives. And that allows us to have a degree of trust in the system, and also allows us to potentially debug the system. So if the system comes up with a wrong answer, and this is a valid chain of reasoning, there must be an error either then in the facts that it believes or in the reasoning steps it believes. So we did an evaluation to evaluate how well the system is doing in terms of providing good chains of reasoning. And what we did was we had users judge whether the conclusions that it came up with clearly followed from the premises, were the premises that it generated and that the system believed, were they correct, were they relevant, did they introduce something new or interesting in the explanation, and then compared with another state-of-the-art explanation system, which they preferred. And so we compared the system against a baseline system. This is another language model called Core. So this is a non-reasoning system that answers questions. And you can see here for this baseline, its explanations aren't very good at clearly showing how a conclusion should follow. This is very typical of current language models. And then the Entanglement writer system does considerably better along those metrics. In particular, you can see about 2/3 of the time, users judge the conclusion clearly followed in a systematic way from the premises it generated. And then in terms of user preferences, as a result, people clearly preferred the explanations coming from Entanglement writer. And I should say this was done in a blind trial where users didn't know which source the explanations were coming from. So this is exciting. Now, I just want to return to one important feature of the way we train the system, which moves me into interactive teachable systems. So you probably remember I mentioned one of the modes we trained the system was to mask out some but not all of the facts that were given. And one of the side effects we found of doing that was when Entanglement writer generates its chains of reasoning, because these facts were necessarily helpful in the training data, it's strongly biased to include those in the chains of reasoning it generates as outputs, including overriding its own internal beliefs. So again, to give an example, and you could think of these extra facts as advice from the user. If I ask the system, do plants require carbon dioxide to make their own food, but I also give it some advice. I tell it, hey, by the way, plants create food through photosynthesis. The system is biased to try and include that in the chains of reasoning that it produces. And this behavior of the system provides an avenue by which we can not only get it to answer questions, but teach it new things. This brings me to the second part of the talk, and talking about how can we actually teach the system. Let me just, there's another question which appears in the chat, which I'm just going to briefly mention as well. So this is from AJ in India. He asks, could this be applied to opinionated conversations or to widely known facts? So that's a great question as well. I'll mention this again in a little bit. For the most part, we've been working with kind of science questions where there's little controversy about the facts and rules, but you can imagine applying this to situations where users may have differing opinions. So for instance, discussion about politics or other topics, where users might want to train the system or to teach the system a particular viewpoint on a topic. And that's exactly what this interaction and teachability should allow people to be able to do. So to give you an idea of what we're aiming for with teachability, let me give you an example here. And this will show how the advice that the user provides can influence question answering. So suppose you give the question, can you pick up a penny with a magnet? And I don't know if you know the answer to this. I actually had to go away and try this. It turns out you can't pick up a penny with a magnet. The system says yes. The user asks why, and the system gives a chain of reasoning showing how its beliefs support that answer. It says, well, I believe pennies are made of metal, metals are magnetic, therefore you should be able to pick up a penny with a magnet. This is actually the incorrect answer. You can't pick up a penny with a magnet, and the user can now argue back and provide some corrective facts. So here the user says, actually, not all metals are magnetic. Copper is not magnetic, and then ask the system to try again. And now by including those user supplied facts as additional inputs along with a question, the system will change the chain of reasoning that it's generated, and now in this case produce the right answer, no, because pennies are made of copper, and here it's reused that user suggestion, copper is not magnetic, and come up with the right answer. So this shows how a user can influence and correct the system's behavior for a particular question. But of course, you'd like the kind of teaching that the users provide here about magnetism to persist for new questions which the system may get in the future. And so the way we do that is to think of Entailment Writer not as a single model, but as a component within a larger system, which also includes a persistent memory of explicit facts. And then, so what happens now is the user asks a question, can you pick up a penny with a magnet? It retrieves some relevant facts, adds those to the context. It generates an answer, for example, here producing that incorrect answer, pennies are made of metal, metals are magnetic. The user argues back, provides some additional information, which is essentially overriding and expanding the system's knowledge, and that gets added back into the memory. And now if the user re-asks the question, we'll retrieve new facts from the memory, hopefully including those corrections the user provided. And now, because of that contextual information, the system revises its answer and if all goes well, produces the right answer here. So you can see here in a simple way, the system has improved its behavior, not by retraining the model parameters, but by expanding and elaborating its external memory, thanks to feedback from the user. So we did a pre-pilot about 6 months ago on some very simple questions about COVID. We chose COVID because this is a topic which is relatively new, and so which the pre-trained model really doesn't know much about. And one sample interaction we had with the system, the user asked, is COVID dangerous? The system says, yes, COVID's dangerous, but it doesn't really know what COVID is. And so it kind of takes a wild stab and says, well, COVID is a kind of wild animal. Wild animals are dangerous. So the user here can now argue back and says, actually, that's not true. COVID is a virus, and that fact is added into memory. And now if the user re-asks that question, again, the system will retrieve facts from memory and use that to help guide its question answering. And now it comes up with a better chain of reasoning. It says, well, now I believe COVID is a kind of virus. You told me that. And I know viruses can cause harm to humans. And so it should follow that COVID is dangerous. And then if I ask a follow-up question, which might leverage that prior knowledge, do masks help against COVID? Again, the system retrieves that relevant fact from memory and now comes up with a better answer. Yes, masks can help protect you because COVID is a virus, and masks can protect you from viruses, and so on. So that's kind of a simple illustration about how the memory is allowing the system to improve on future answers. So there's another question. These are, by the way, these are great questions that people are asking here. So Stanham asks, will the system get the answer only if the relevant data is in the memory? And what if the system doesn't have the relevant data in its memory? So that's a great question as well. So if the most of the chains of reasoning here are being generated with facts that are coming from the system's own latent knowledge. So most of the answers it will get right, and it'll get right because the things it already knows. The role of the memory is not to provide all the knowledge, but to augment and correct errors in the system's knowledge. So if the system already has the knowledge to its pre-training, it will get the answers right, and there's no problem. And I'll give some examples of that. If the system has an error in its pre-trained knowledge, it's correct. We're dependent on the retrieval mechanism retrieving the correction to that knowledge, or in this case with COVID, retrieving some extra knowledge that the system doesn't have in order to do the correct reasoning. And yes, there is a potential failure point here. If the system fails to retrieve that knowledge and it doesn't know it already, then of course it can get the answer wrong. And then somebody also asked, does the system say, I don't know the answer? Yes, indeed it does. If I ask a question, for instance, a true-false question, and the system can't prove the hypothesis, and it can't prove the negated version of the hypothesis, it'll say, well, I can't prove anything, and then again ask the user for help to provide some help. And again, I can show an example of that in just a second. Again, these are great questions. So we have a simple live interactive version. We don't make any claims for the interface. It's kind of a bit clunky, but I'll just show it to you anyway. So users can enter questions, like here the users entered a question: can a suit of armor conduct electricity? The system will show its answers. So here the system said, yeah, I believe it's true because metal's a good conductor and a suit of armor is made of metal. The system will also list its retrieve facts. Here it didn't find anything relevant, so it just worked from its own latent knowledge. And then kind of at the bottom here, this is more for us debugging it. It gives a trace of its reasoning. So here, what you can see here, the system tried to prove, first of all, a suit of armor can conduct electricity. It found a chain of reasoning. That's the one that's shown in blue here. It also tried to prove the opposite. It tried to prove a suit of armor cannot conduct electricity. It came up with a chain of reasoning here. Metal is an electrical insulator. A suit of armor is made of metal. But then when it checked, it said, well, actually, I don't believe metal is an electrical insulator. And so it threw out that particular chain of reasoning. So that's just gives you a little inkling about what's going on behind the scenes here. And so I'll just show you a quick video of the live system. So here the user's entering a question here. Again, a variant of the one I just showed. Can a magnet attract a penny? They click ask. The system gives the wrong answer. Magnet can attract a penny. And here's its proof: a magnet can attract magnetic metals, and it says a penny is made of magnetic metal. The user here clicks no. It doesn't agree. The user doesn't agree with the answer. And at this point, the user is given the option for entering some advice or correction here. And so here the user is trying to give a bit of help and says, actually, penny is made of copper, and clicks use it. And now the system will try again with that knowledge. again, the systems still come up with the wrong answer. A magnet can attract a penny. It's used the user's suggestion here, so it's learned a penny is made of copper. But you'll see in the second line, it still thinks a magnet can attract copper. So the user can correct that by clicking on, but it's not true. And what that does is cause the negation of this fact. So to be added to memory. And that's what happened when the user clicked it. And now the system's revised its reasoning and said, oh, actually, now I've changed my mind. A magnet cannot attract a penny. A penny is made of copper. A magnet cannot attract a copper. Therefore, a magnet cannot attract a penny. And so finally, the system's got the right answer. The user now clicks agree, that they agree with the answer. And those things the user's taught have been added to the memory. So at the bottom here, you see the system's learnt a magnet can't attract copper, penny is made of copper, and so on. And then finally, just to show the system's use of that knowledge for a new question, if I ask, can a magnet pick up a copper pan, and click ask, the system uses that retrieved knowledge to come up with now a good explanation. A copper pan is made of copper, a magnet can attract a copper, therefore a magnet can't pick up a copper pan. So this just shows you the style of reasoning which the system can go through. I'm just going to, there's another question which appeared in the chat. Somebody asks, so Stanham asks, some questions can have ambiguous answers. For example, the type of metal that an armor is made of is ambiguous. So can we ask the system to prompt the user to give some more information? This is another great observation. So it's true the system is working with some degree of abstractions here. You know, a copper pan is made of copper. I guess that's universally true. A magnet cannot attract copper, but there are some facts, like a suit of armor is made of metal, which is generally true, but maybe not always true. So currently the system doesn't know about variations. I think that would be a great idea for the system to be able to ask for clarification from the users. And for instance, that could happen if when the system checks whether it believes a fact, if it says, well, I believe it, but I'm not completely sure, that could be a cue, for instance, for the system to ask for clarification questions. So I think bottom line, that would be a great suggestion. We don't have a mechanism to be able to do that at the moment. So how well does the system work? And so I'm just going to give a quick summary of experiments we did with the system, both using simulated feedback and real feedback from the user. So for simulated user feedback, what we did was we took established data sets. We then had a simulated user interact with the system on the training set. And the way this works is each training question is given to the system. If the system gets it right, we don't do anything. If the system gets the answer wrong, then we simulate a user giving some corrective feedback, and that goes in the memory. The memory gradually grows with time. And then after the system's worked through all the training cases, we take the simulated user out of the loop and then run the system on the test questions to see whether it's actually being taught something by the user in the training set that is useful for the test problems. So as an example, so here's a question that Entanglement Writer gets right. So air is considered to be a vehicle for what? Light, wind, speed, or sound. The correct answer here is annotated as sound. And the system comes back with the explanation, well, air is a matter made of air particles and sound requires matter to travel. The simulated user says yes, and so that's all that happens here. If Entanglement Writer gets the answer wrong, the simulation works a bit differently. So an example is this one: spiders catch prey with a silky thread, and so on. Silky thread is the desired answer. Entanglement Writer actually gets the wrong answer here and tries to convince the user. So spiders catch prey with trickery, because some animals catch their prey with trickery, and a spider is the kind of animal. So it's not a terrible line of reasoning. Here, the simulated user says no, Now, what do we use as simulated feedback from the user? Now, in the data sets we worked with, they happen to be annotated with facts which support the correct answer. So this is very convenient. We can use one of those facts here to simulate the kind of thing that a user may offer back to the system as correction. So here we take the fact a spider web is used to capture food by spiders, and Entanglement Writer says, oh, that's great to know, I'll make a note of it in my memory. And then we work through in simulation all the training questions, and the memory down here fills up with corrections and additional facts from the user for all the questions it gets wrong. And then when that simulation is finished, we then run Entanglement Writer, still with its frozen parameters, through the test questions, but using the user-entered beliefs. And so how well does it do? If we just run a standard AI high-performance question answering system on our data set without any explanations, we get around 75% on both of those. When we run Entanglement Writer, our system that generates chains of reasoning, it doesn't do quite as well out of the box on this test data. However, after getting user feedback on the training questions, we find after teaching, its performance goes up significantly, including above the level that the original highly trained model performed. And we could say, well, what's the upper bound? Suppose we were to give feedback on every single training question in the data set. And we found this is pretty close to the upper bound on the system, getting close to the upper bound would be about 78% for one data set, and we're close to the upper bound on the other data set. And so I'm just going to finally jump ahead and just briefly mention experiments we did with real users. This was a very small scale trial. We took 31 questions from our data sets, which the Entanglement Writer system really struggles with, so it gets most of these wrong. We, again, similarly divided them into 5 training questions for users to work with, and then 28 hidden test questions. And then the task we set the users was to try and teach the system facts to get the training questions right, and then we would evaluate them on the hidden test set. And before interaction, as I mentioned, Entanglement Writer struggles with these questions. It gets about 20% on the training questions, 38% on the test questions. But after we interact with the system, users interact, we find, perhaps not surprisingly, the system does almost perfectly on the training questions. So in pretty much every case, users were able to teach the system new things, allowing it to get the questions right. But perhaps more significantly on the test set, the performance goes up by nearly 20%. So this shows evidence that the system, the users have not just debugged particular problems, but the system's learned something which persists through to the test set. And so this suggests a simple cognitive architecture where instead of just having a black box model, we'll have a frozen neural engine which can do one-step reasoning. We have a controller which can assemble these into reasoning chains. And then we have a memory of user feedback, which will augment and override innate system beliefs. So it gradually learns new facts about the world on the fly during interaction. So I'm just finally going to end here and just give some quick reflections. So I've shown we can build systems that can generate reasoning chains that both reflect a line of reasoning showing how the answer follows from things the model knows, and also chains that are truthful. In other words, the statements the system's giving are actually things which the system believes itself. And as I mentioned, one of the amazing things of language models is we don't have to provide all this knowledge explicitly. Most of what Entanglement Writer is building its chains from are innate beliefs that it's picked up during pre-training, and the additional memory contains augmentations and overrides which the user's provided to extend that. And as I say, this opens the door to a super exciting world in which we might be able to teach the systems not by throwing thousands of training examples with it to it, but having a kind of dialogue and interaction with the system, as I've shown. And if you want to find out more, you can Google Entanglement Bank at AI2, or you can Google Towards Teachable Reasoning Systems. This is an archive paper we're about to release. But this last query, you'll have to query after this coming Thursday, because the paper's only going to be released tomorrow, if you'd like to know more. So with that, I will stop, and thank you so much for your attention, and thank you for the great questions. And
great.
Bill, sorry, go
just
ahead.
yeah, just quick reminder. Great, thanks a lot for the presentation, and I see we have questions in the chat. And remind everyone, if you have questions, feel free to type in the chat, or raise your hand to ask questions. I can unmute you. Please go ahead.
Yeah, and Bill, I'll leave you to just interrupt me when I need to stop. Yeah, so there's a couple of new questions that have appeared. So one question is, how do we prevent results of one question being impacted after some feedbacks were given for another question? So that's a really good question. In the very early version of the system, we did actually find this kind of interference. We would find the user would volunteer some facts for question B, and these might adversely affect the answer that we're given for question A. So what the system now does is, once the user notes that it agrees with a particular answer, it will make a note that the facts that were used in a particular chain of reasoning that came out of the system's memory were actually approved by the user, and that the chain of reasoning was approved. So in other words, this guarantees reproducibility, that given a new question, given that if you re-ask the same question again, it will use that same chain of reasoning. So there's some kind of persistence, not just in the knowledge, but in the chain of reasoning that was approved. So that's a great question. Another question, so this is from Bodhi in the USA. So for the simulated feedback on the wrong cases, is it reinforcing some training examples? So essentially what the simulated feedback is doing is it's not quite reinforcing training examples. It is providing corrective information that is meant to cause the explanation and the chain of reasoning for an incorrect answer to be changed to a correct answer. I guess one thing I should say is, at least during our simulated training, we don't actually check that user feedback does debug the problem. And so there's an approximation in that simulation that the simulated feedback does actually debug the error. And as you showed in the demo I showed, sometimes when the user offers feedback, it doesn't fix the problem. The system may go off and provides a second incorrect chain of reasoning. So the interaction may go several times, and that's one of the limitations of simulation, is that we don't actually model that. So yeah, that's a great question. Somebody else asks, curious, is the model using a graph neural net or a symbolic knowledge graph or something else? That again is a great question. No, the model here is simply a text-to-text model. So the input is a text question and possibly a context, and the output again is a set of texts that describe the chain of reasoning producing the answer. You could imagine assembling these chains of reasoning into a big graph and then doing some reasoning over that graph structure explicitly. This system doesn't do that. That would be a super interesting line of reasoning as well in future. So given all these chains, can either a neural system or maybe even a symbolic system reason over that graph of facts and connections between them? But we haven't done that. Another question is from Martin: should reasoning capabilities be added as part of the creation process of language models, or is your post-processing way a better option? This is a really good question as well. There's basically two ways of trying to get a language model to reason. The first is, let's try and shovel the reasoning into the language model itself. So we're going to train it on full examples of reasoning, and then hopefully as outputs, we'll get nice reasoned answers. As I mentioned at the beginning, we tried doing that and it didn't work very well. Some of you may be familiar with some earlier work we did at AI2 on a system called Rule Taker, where we showed actually you can actually train a language model end to end, at least in restricted domains. So all the reasoning capabilities are built into the language model. So I think the answer is yes, you can train a language model end to end to do this kind of structured reasoning up to an extent, but on fairly limited size problems. When you get to larger problems, like some of these real life ones, my personal belief is it doesn't work to try and get a language model to do everything. And in fact, even if it did work, it doesn't give you a handle on exploring and modifying those proofs. So, you know, the alternative proof is the one, the alternative approach is the one I've chosen here, where we use a language model for the basic inference operation and then wrap a controller around it. But I should say that the jury's out on this, and people are exploring both lines of attack on how to do reasoning. And as I say, you know, in this version, we're going for an external control loop around the language model. And then Sasha asks, again, this is a great question: how do we handle conflicting facts, such as the one user says coffee is good for us, and then another user says coffee is not good for humans? So I think that is another great question. We've discussed about, you know, if we put this system on the web and collected lots of information from the users and built up a knowledge base, how do you handle that kind of growing knowledge base, particularly when there's conflicts? One approach with this would be to allow users to essentially create their own persistent memory reflecting their own beliefs and views about the world. So I could teach the system, you know, my perspective on a particular topic. Somebody else could ask about a different particular topic and have their own separate memory. It would be nice to have a kind of growing knowledge base about kind of consensus views of the world. And of course, then there is the problem of conflicting beliefs and conflicting opinions. This is nothing new, of course. This is something, for instance, Wikipedia has had to wrestle with. And so policing mechanisms like have been used in Wikipedia could be used to try and police different opinions and represent those and moderate contributions to a growing knowledge base like that. So for instance, Wikipedia will restrict entries about controversial topics like politics and so on, and police that. But yeah, that's absolutely a good question. Or you could imagine a system with different opinions, maybe having two entailment writers talking to each other, where different versions of the system have different sets of beliefs from different users, and have two systems converse like that. And then Zuhang asks, do you validate the knowledge that is sent back to memory is actually correct? This is another really good question. So the short answer is we don't do that. But one of the extensions we're working on is to try to validate knowledge not just with feedback from the user, but using an external authoritative source of knowledge. So for instance, a textbook, or maybe authoritative sources on the web. You know, I mentioned the system tries to check that the generated statements are things it actually believes. But you could imagine the system could also go out on the web and say, well, I kind of believe that COVID's a wild animal, but before bugging the user, let me go out on the web and see whether there's also evidence for that. So yes, we certainly could bring in external knowledge sources as another source of correct authoritative knowledge, either to check the system's beliefs are correct, or even to check that the things the user's entering are correct. Again, this is an area for future work that we haven't explored yet, but that's a great suggestion.